In this video, we're going to return to stoichiometry and we're going to add in the gas laws as a way of finding moles or converting from moles in our stoichiometry problems. So first of all, let's return to Avogadro's law. So recall that based on Avogadro's law, 1 mole of a gas occupies the same volume as 1 mole of another gas at the same temperature and pressure. So no matter what the gas is, if there's 1 mole of it, it's going to occupy the same volume as 1 mole of any other gas. So as a result, when you're solving stoichiometry problems that involve converting between the volume of one gas and the volume of another, you can use volume ratios. So if we look at an example, so here's an example where everything is a gas. So you have hydrogen gas reacting with oxygen gas to make water vapor. So because everything's a gas, and we're going to assume we're staying at the same temperature and pressure, we have the mole ratios. So there's 2 moles of hydrogen to 1 mole of oxygen to 2 moles of water. But these can also be volume ratios because they take up the same volume. So 2 volumes of hydrogen gas will react with 1 volume of oxygen gas to make 2 volumes of water. So if we look at an example, so here's another reaction where everything is a gas. We have nitrogen gas reacting with hydrogen gas to make ammonia. So for that reaction, if 3 liters, which is a volume, of nitrogen gas is reacted with excess hydrogen gas, what volume of ammonia gas is produced? So we start with the volume given in the question, the 3 liters of nitrogen, and then we can use our ratio. The same ratio we've been using as a mole ratio can now be used as a volume ratio. So we take the coefficients from the balanced chemical reaction. There are 2 ammonia for every 1 nitrogen. So we can cancel out the nitrogen, and so we find that 3 liters of nitrogen would produce 6 liters of ammonia. So here's our stoichiometry roadmap that we have so far. So now we're going to add in the gases. So the first part, so if we have the volume of a given and we need to find a volume of an unknown, where they're both gases, we can go straight across. So we don't even need to get into this mess. We can just use the ratio from the balanced chemical equation. So that's the first part. So to solve stoichiometry problems that are a bit more complex, right? They involve gases, but they're not simply volume questions. We're going to need to incorporate the ideal gas law into what we've learned previously as another way to find moles, right? So we know that the moles are the foundation of our stoichiometry. And remember that ideal gas law, PV equals nRT, that N is moles. So when you have all that other information about the gas, you can find moles. Or if you have moles, you can find the volume. So if we look at our map, right? So now when we have a volume of a gas given, we can get to moles using the ideal gas law. Or if we need to find the volume of an unknown gas, we can convert from moles to that volume using the ideal gas law. So let's look at an example. Ancient alchemists like to use strong sulfuric acid to produce dramatically dangerous effects. One interesting reaction occurs when sulfuric acid reacts with iron metal to produce gas and an iron 2 compound. What volume of gas is produced when excess sulfuric acid reacts with 40 grams of iron at 18 degrees Celsius and 100.3 kilopascals? So here's that reaction. So the iron's reacting with the sulfuric acid to make hydrogen gas and iron 2 sulfate. So if we look at the question, it says what volume of gas is produced? So it's asking for the volume of hydrogen gas that's produced. That's our unknown. And we have 40 grams of iron to start with. So if we look at our roadmap, we've got that 40 grams of iron, so mass of given. We're trying to get to a volume of hydrogen gas, so over there. So the path we're going to take is we're going to go to moles using the molar mass like we've done many times before. Then we're going to use the mole ratio to get to the moles of unknown, which is hydrogen gas. And then we're going to find the volume using the ideal gas law. So there's the reaction again. I'm just going to put down the information from the question. So we have a mass of iron of 40 grams. The molar mass of iron from the periodic table is 55.85 grams per mole. We also know that the gas is at a temperature of 18 degrees Celsius, which we have to convert to Kelvin, 291. And we're told that the pressure is 100.3 kilopascals, and we need to find the volume. So the first step is to find the moles of hydrogen gas produced using stoichiometry. So this is really two steps in one. So we're going to take the 40 grams of iron. We're going to convert that to moles using the molar mass. And then we're going to convert to hydrogen using the mole ratio from the balanced chemical equation. So units cancel and we're left with moles of hydrogen gas, which is what we're after. And so we have 1.074306 moles of hydrogen. So now that we have the moles, or the N, we can use the ideal gas law to find the volume. So PV equals nRT. We're trying to find V. So V equals nRT over P. And there we've plugged in all the numbers, 1.074306 moles times 8.314 kilopascal liters per mole Kelvin times our temperature of 291 Kelvin divided by our pressure of 100.3 kilopascals. So we get a volume of 25.9 liters. So that's our final answer. So let's look at another example. If 3 liters of oxygen gas reacts with 3.50 grams of aluminum metal at 98.2 kilopascals and 24 degrees Celsius, what mass of aluminum oxide is produced? So here's our reaction. We've got a mass of aluminum of 3.50 grams, and there's our molar mass. We have a volume of 3 liters for oxygen. We also have a temperature of 24 degrees Celsius, which we need to convert to Kelvin, and a pressure of 98.2 kilopascals. And the question is asking us to find the mass of aluminum oxide. So there's a lot more information given here. In fact, there's information given about 2 reactants. So what does that make this? It is a limiting reactant problem, right? So we have information about both reactants, so we have to figure out which one is the limiting reactant. So here's all that information just carried forward. So to figure out which one's the limiting reactant, we're going to find the number of moles of each reactant that's available. So first of all, the moles of aluminum. So we've got a mass of aluminum. We're going to use the molar mass to find out that we had 0.12973 moles of aluminum participating in the reaction. For oxygen, we want to find moles. We're going to use the ideal gas law rearranged. So N equals PV over RT. We're going to plug in all the information that we have. We have the pressure and the volume and R and the temperature. So we plug all that in and we're left with moles. So we find that we had 0.11931 moles of oxygen. So those are the amounts that reacted. So I've just carried those forward here. So remember, we're still trying to find a mass of aluminum oxide. So now we're going to find the number of moles of product that each reactant could produce. So the aluminum, we use the mole ratio from the balanced chemical equation, so it's a 2 to 4. So if all the aluminum reacts, we could make that much aluminum oxide, 0.064865. Then we take the moles of oxygen, convert that to aluminum oxide. This time the ratio is 2 to 3. So if all the oxygen reacted, we could produce 0.07954 moles of aluminum oxide. So this tells us that the aluminum is the limiting reactant because it can produce less aluminum oxide. So that's the amount of moles of aluminum oxide that are actually created. So finally, we're going to take that number of moles. We're going to use the molar mass of aluminum oxide to find the mass. So there's the moles times 101.96, which is the molar mass, which gives us that we produced 6.6 grams of aluminum oxide in that reaction. So just in case that wasn't enough, we're going to add one last twist. So when you're carrying out a reaction and you're making a product that's a gas, often that gas is collected by letting it bubble up through water into a container that's filled with water. So there's water all over the place. So what happens is some molecules of water vapor will mix with the gas that you're trying to collect. So the gas that you're collecting isn't completely pure. It's got some water vapor in it. So to avoid that error in the calculations, when a gas is collected over water, you have to correct the pressure before you can use it in the ideal gas law. And you do that using Dalton's law of partial pressures. So recall that law stated that the total pressure of a gas is made up from adding all the partial pressures of whatever gases are in that solution. So in this situation, the total pressure is going to be the pressure of the gas that you're collecting plus the pressure of water vapor. And so the partial pressure of water vapor has been determined, and it's the same for any gas that's collected over water at a particular temperature. So this table shows you the partial pressure of water at different temperatures. So you'll need to consult this table whenever you come across a question where the gas is collected over water. And there is a similar table in your textbook on page 558. So let's look at a sample problem where this becomes important. A student reacts magnesium with excess dilute hydrochloric acid to produce hydrogen gas. She uses 0.15 grams of magnesium metal. What volume of dry hydrogen does she collect over water at 28 degrees Celsius and 101.8 kilopascals? So that's the key words, over water. If you see those, that tells you you need to account for the partial pressure of water. So here's the reaction that we're carrying out. Let's put down the information that we are given. So we have a mass for magnesium, 0.15 grams. We're trying to find a volume of the hydrogen gas. There's the molar mass of magnesium. So the hydrogen gas we know is at 28 degrees Celsius, which we convert to Kelvin. And we're told the total pressure is 101.8 kilopascals. So because it's collected over water, we have to take into consideration the partial pressure of water. So if you look at that table and you look at 28 degrees Celsius, because that's what temperature we're at, you find that the partial pressure of water is 3.78 kilopascals. So that means that the pressure of the hydrogen only is the total pressure, the 101.8, minus the pressure contributed by the water, 3.78. So that gives us a partial pressure for hydrogen gas of 98.02 kilopascals. And that's the number you have to use in the calculation. So other than that additional subtraction right there, this question is no different than the one we did earlier. So the first thing we're going to do is we're going to find the moles of hydrogen that are produced. And we're going to do that by finding the moles of magnesium first and then converting to the moles of hydrogen. So we have 0.15 grams of magnesium. We use the molar mass of magnesium to get to moles. And then we use the mole ratio, which is 1:1 in this case. So we find that 0.15 grams of magnesium would produce 0.0061703 moles of hydrogen. Now that we have moles of hydrogen, we can use the ideal gas law to find the volume of hydrogen. Okay, so there's our moles. So to find the volume of hydrogen, we're going to rearrange the ideal gas law for volume, which looks like that. We're going to plug in all the numbers that we have, remembering to use the partial pressure of hydrogen as our pressure, that subtracted one, and not the total one from the question. And when you calculate that out, you get an answer of 0.16 liters. So there you have gas law stoichiometry.